Hi folks, welcome back to Tori Explains. In this video, we're going to go over how to use separation of variables to solve a differential equation that is a logistic model. And stay tuned because at the end of this video, I'm going to show you how I use Mathpix to put my handwriting into an elegant form that I can use to submit to my teacher. All right, so first off, let's get straight into it. So I'm going to start with the differential equation. My change in population with respect to time is equal to 0.001 times my population, all that multiplied by 3,000 minus my population. All right, so the first thing I'm going to do is just rewrite this form a little bit. So I'm going to rewrite this as my change in population with respect to time is equal to 3p minus 0.001p squared. All right, now I'm going to do my separation of variables. So I see that I have a p over here and I have p's on this side, and then I don't have any t's. So I'm going to pop this whole term down into my denominator and then move my dt over. So what I get after doing that is dp over 3p minus 0.001p squared is equal to dt. Now I'm just going to factor out a p in my denominator here to make this integral a bit easier. So what I get when I do that is p times 3 minus 0.001 p squared. All right, so now in order to solve p, what I need to do is integrate both sides. So when I do this integral here on the left, this is just the form of this integral is telling me that I should be doing partial fraction decomposition. So I'm going to want to rewrite this into some form that has some a term over p plus some b term over my 3 minus 0.001 p. All right, and I realized I actually left this as a p squared. That should become just a p. All right, so now that I have this form, I could say that I want a times 3 minus 0.001p plus b times p. And in my numerator over here, I just have a dp, so that's really the same as saying 1 dp. So that means all this stuff here must be equal to 1. All right, so now when I set p to 0, that'll go to 0, and I get a equals 1/3. And now when I set p to be 3,000, that would go to 0, and then I'd get that b should equal 1 over 3,000. All right, so now I can actually go back to doing this integral. So when I have a, which I said is 1/3, over p, that's just 1/3 ln p. And then I have, well, so here in my denominator, I have 3 minus 0.001p. So that would be my b term, which is 1 over 3,000 times negative 1 over 0.001. And then that'll be ln 3 minus 0.001p. All right, so now what I can do with this coefficient here is that I know 3 or 1,000th of 3,000 is just 3, and then this will all become negative. So just to make this a little bit easier, I'm going to convert this into a 1/3. All right, and then now I have to integrate the other side of my equation. So then on the other side, I'll just get t plus c. All right, so now let's rewrite this a little bit. So I'll get 1/3 ln, and then using my log rules, I get p over 3 minus 0.001p. And that's equal to t plus c. I'm going to multiply my 3 over just to clean this up. So I'll get 3t, and then 3 times c is really just another c, so I'm not going to rewrite that. But now what I'm going to do is plug in my initial condition. So at this point, depending on which initial condition you were using, you could use that to solve for p. So in this particular question, I was given that at t equals 0, p equals 50. So p of 0 is equal to 50. All right, so let's plug all that in. I'll get ln of 50 over 3 minus, well, 1/1000th of 50 is just 0.05, and that'll be equal to c. All right, so there's my c term, and I can rewrite this on my denominator as just 2.95, just to keep things easy and simple. So now what we're going to do is I'm going to solve to isolate this p, so it's by itself. So what I get is I can raise e to all this stuff on that side to get my stuff in here. So I get p over 3 minus 0.001p is equal to my c term, which is ln, or I'll do it like this. So e plus 3t and then plus ln 50 over 2.95. So now, because I have this multiplication sign here, using my exponent rules, I can clean this up even more to say p over 3 minus 0.001p equals 50 over 2.95 times e to the 3t. Because when we are adding in our exponents, where it's the same as multiplying them with the same base, and then I just cleaned it up a little more. So now what I want to do is actually isolate these p's here. So what I'm going to do is multiply all of this over. So I get, after doing that, that p is equal to 150 over 2.95 e to the 3t minus, now I would have 0.05 over 2.95 e to the 3t p. So now I'm going to add this term over. So I get p plus 0.05 over 2.95 e to the 3t p is equal to my 150 over 2.95 e to the 3t. All right, now we're almost there. What I have left to do is factor out a p. So I get p, which is 1 plus 0.05 over 2.95 e to the 3t equals all this stuff here. So I'll just go like this. So I'll just reuse that there. And so that's all equal. Now when I divide that over, I'll go over here to do that. I get p equals 150 e to the 3t over 2.95, all divided by, now I'm just going to rewrite this a little to make it a bit easier to simplify. So I'll get 2.95 plus 0.05 e to the 3t over 2.95. Now this will clean up very nicely. So I get p equals 150 e to the 3t over 2.95 plus 0.05 e to the 3t. All right, so now typically what you see is 1 plus something with an e to the negative lkt. That's kind of the form that you would get based on the sort of formula that you'd use for this type of differential equation. But let's go over how you'd actually get to that. So what I'm going to do is I want to turn this right here into a 1. So I'm going to multiply by 1 over 0.05 e to the 3t over 1 over 0.05 e to the 3t. All right, so now what I get is I have, so 150 divided by 0.05 is equal to 3,000, and then those e to the 3t's will cancel out, and then 2.95 divided by 0.05 is equal to 59, and then I have times 1 over e to the 3t, which I can write like this, and then obviously that other term will just become a 1. All right, so this is it. This is your p of t. I'll write that a bit nicer. So this is your p of t that you can use as your function for your population as a function of time. All right, so now let's go over how I would submit this to my teacher using Mathpix. So first, I'm just going to exit presentation mode, or actually I'll go like this. So I'm going to airdrop to my computer. Now I'll share my Mathpix. All right, so first I'm going to airdrop this note to my computer. So I have this note here, all right, and it's called logistic integral. So what you're going to do is click this plus sign up at the top and then go upload. All right, and so now where to go. Actually, I'm going to go like this. Here we go, with a PDF. So I'm just going to drag and drop this. All right, then we go open, and that name will work. All right, so now this is going to convert everything into a nice, pretty form that I can use to submit. So let's see. All right, so this is all my work. All right. Okay, here we go. So now you can see that I've converted this all into a nice, pretty form. It was just this one part right here, but I can go ahead and actually just delete that. All right, so that'll clean that up nicely. I wanted to show you how I was able to easily clean up just a few little things that I wanted to slightly change. So luckily, it's really easy over here to just go through and change little things, like say I wanted a to not equal 1/3 and I realized, whoops, it should have been 1/4. It's super easy to change that, and then you can just change it right back. And so luckily this is super user friendly, and now my math is exactly how I want it to look. So this is the preview of what I'll actually be submitting, so you can see it's a super nice way to present every step that I went through and really nicely show all the work I did to get to my answer. Bye, y'all.